Hey CW Apes, Mr. Kennedy here. These are your Chapter 3 notes on critical thinking, science, models, and systems. Today we're going to dive into the strengths and limitations of models by studying the basic answer to a very simple question: what is science? And as we do that, we're going to learn a little bit about a people group who used to live on Easter Island called the Rapa Nui. By the time I'm done today, I'm going to tell you the story of this group, and what I want you to be able to do is to describe the working parts of the system that is Easter Island and pick out positive feedback, negative feedback, time delay, and synergy. So let's begin. Okay? First thing I want you to deal with question-wise is, what is science? I know, it's a class I have to take to graduate, Mr. Kennedy. No, that's not what I mean by what is science. Nor do I want you to all of a sudden list all of the steps of the scientific method here. What is science is all about you understanding that science is a process. It's a process producing knowledge methodically and logically. And it depends on us being able to make precise observations of natural phenomenon. Realistically, science is the cumulative body of knowledge produced by many scientists working together in a variety of fields to help us understand how the natural world works and to meet the practical needs of everybody in society. Science depends on a lot of things. Here's one of them. Science depends on accuracy and skepticism. Scientists are naturally skeptical, which means that if we see something going on in the world around us, we're not just going to accept it for face value without us first performing some sort of test or experiment to try to figure out or validate what we're seeing. Scientists are also unbiased. That means that whatever we see going on in nature, we don't apply our personal opinion to it. We don't use the words I think or I believe in any of our descriptions because we want to be open to any and all possibilities. Scientists always strive for accuracy, correctness in their measurements, and reproducibility. So whatever we're doing, we want other people to be able to do too, to add validity to any claim that we might make from a test that we're running. To kind of give you a flow of how things work in science, I put this little concept map together for you. Typically, science starts by identifying a question, and as you learned in the steps of the scientific method, forming a testable hypothesis, testing it, interpreting those results, and then making a decision. Does my data support my hypothesis? Awesome. If it does, you can go on to peer review. If your data does not, then what do we need to change in order to further explain whatever it is you're seeing? Okay? So, like the analogy that I used in freshman bio was like, hey, I can't find my cell phone when I get up in the morning. So what do? You make a hypothesis that says, well, maybe I left it in my backpack. So you go look there. If it's in your backpack, great. Okay? You're done. But if it's not in your backpack, you got to revise your hypothesis and then test that hypothesis so that you can answer the question of, hey, where's my cell phone? Okay? Science also involves a lot of inductive and deductive reasoning. Deductive reasoning is a logical reasoning from very general things down to specifics. So you start off with broad, sweeping claims that lead you to a specific idea. Inductive reasoning is basically the exact opposite. Okay? So you start with many specific observations that ultimately produce a general rule. It's also important to recognize that, you know what, in terms of science, there's something to be said for insight, creativity, aesthetics, and blind dumb luck. Take the guy who discovered penicillin as a big fat for instance. Blind dumb luck caused his petri dishes to grow mold on them while they were sitting, on his counter over the weekend, and the rest is history. Hypotheses and theories are at the heart of the scientific process. So basically, we see a question, we make a hypothesis, which is a testable explanation of that question. After going through the steps of the scientific method you learned in a different lecture, right? If our data supports our hypothesis, we can end up with a scientific theory. That theory ultimately is a hypothesis that has withstood repeated testing over time, or as it says there, it's supported by a large number of tests, and subsequently is considered by experts to be reliable. How do we get to that reliability phase, or that point at which other people like agree with what we're saying? Well, we have to manage some things like probability in order to do that. Probability is the measure of how likely something is to occur. So there's two ways to look at probability with regard to our scientific theories. We either want a high probability that what we're saying is true, or a low probability that the opposite of what we're saying is true. It's kind of how it works, right? So scientists try to increase confidence in the study that they're doing by comparing the results that they got to random samples or to a larger group to help increase the probability of what they are saying as being true. Okay? So that leads us to statistical tests. I was once told in a statistics class that realistically you can make numbers say whatever you really want. I'm not going to bore you with details on all the different kinds of statistical tests that are out there, but what I will say is depending on the test, your level of confidence or the percent of confidence that you get from number crunching will change. Statistical tests tend to focus on calculating the probability that the observed results could have occurred by random chance. So what that means is whatever you did in your experiment, like you need to decide, did it happen because of your experiment, or did it happen just because of random chance and blind dumb luck? To give you an example, in an ecological test, we don't consider the results of the test significant unless the probability is less than 5%. What does that mean? That means that there is a less than 5% chance that what I'm seeing happened as a result of blind dumb luck or random chance. And 95% probability that whatever happened was the direct result of the experiment that I ran. Okay? When it comes to the experiments that you do run, you do have some options. You can do a natural experiment, which involves observation of events that have already happened. You could do a manipulative experiment or a controlled study, which are the kinds of experiments you're probably most familiar with from like your biology and chemistry classes and things like that, where some conditions are deliberately altered and all the others are basically held the same. You can do blind or double-blind experiments, and those are really, really important if you're going to test anything on people. People are super smart, and sometimes you could give them a like sugar pill and tell them it's super powerful medicine. And you've heard the whole idea of mind over matter. Well, hey, like you could give somebody a sugar pill and you tell them, hey, this is super powerful medicine. It's going to take all your pain away. And because they believe it's super powerful medicine, even though it's just a pill made out of sugar, like magically the pain goes away, right? So you almost have to lie to the person who's in the study as well as sometimes the researcher, so that there are no like unconscious cues given to the people that are participating in the study that could skew your results. Variables. All right, so in each study, basically there's one dependent variable and one or more independent variable. The key to these variables is that no matter what kind of experiment you're running, you have to keep these controlled, right? And you have to identify them. You got to know what your dependent, independent variables are at all times. Not only will that help you get validity in your experiment, but it's even going to help you with your number crunching. When you graph these things, the dependent variable is always on your vertical or y-axis, and your independent variable is always on the horizontal axis. All right, so that's experimental design. That brings us to a point where we can start looking at models. All right, so a model is a simulation of a system being studied, right? And sometimes what we need to look at is such a big concept or a grandiose thing that like there's no way we could like run an experiment on it, in a lab. I've got a picture here of the America's Cup sailboats that used to sail regularly in the San Francisco Bay. The idea of the America's Cup sailboat was obviously to have like the fastest boat possible. But it's really hard to control the environment and to run experiments on your boat when you're dealing with a massive space like the San Francisco Bay. So rather than do that, you can build a smaller model of the boat and test it in a controlled environment, almost like a swimming pool or an indoor swimming pool, and make all of your tweaks and your modifications as needed to get a boat in that small environment that goes super fast Then you take all those tweaks and you apply them to the big boat, and you should get a really, really fast moving boat. All right. Models are simple representations of phenomenon. They can be physical, they can be model organisms, they can be mathematic. There's all kinds of models that we can make. But ultimately, what the model does is allows a scientist to study a complex system and predict the effect of conditions that are just too difficult to recreate and to control in any other way, right? Oftentimes, it takes lots of models before scientists can gain any confidence in what they're doing. That leads us to kind of a different form of a model, a system. Okay, so we can model a system in a lot of different ways. This is a picture of a system, which is a group of interacting elements that form a complex whole. So each part of a system could actually be modeled, and we can do experiments on each part of a system to learn more about how the greater whole works. Now, if you were paying attention earlier, if we're doing parts on small pieces to then understand the bigger picture, that's a form of reasoning that I laid out for you at the beginning. Do you remember what it was? Okay, so let's go through what it means to be a system. All right, so systems are often networks of interdependent components. They're networks of components and processes with materials and energy flowing from one component to the next. Basically, they're a central concept in understanding how environmental science works. Here's some examples: an ecosystem, climate systems, geologic systems, economic systems. These have interdependent components that support one another and oftentimes have energy flowing between them. So in order to understand what's going on with climate, we need to understand what's going on with all the working parts that create and feed into climate. Just like an ecosystem. In order to understand an ecosystem, we can't just start at the top and go, yep, that's how the ecosystem works. We got to start with the individual animals in that ecosystem and then build from there. Components. So there's lots of components of a system. And basically, when you think about the components of a system, one of the most important things to do, again, is to look at variables, right? Like state the variables. Like store sources like, matter or energy, or like the variables can have like specific pathways through which the resources move from one state variable to another. Like, we need to be able to nail down what those variables are, like how materials are moving, especially like energy through a system. Systems can be open or closed. If you have an open system, then you're going to exchange matter or energy with your surroundings. If it's a closed system, then it's self-contained, so you don't exchange any matter or energy with the outside. Think about the Earth. Where are the open and closed systems on the Earth, or in the Earth, I should say? The Earth, in and of itself, in totality, is a closed system for pretty much everything except for light or energy, as you might want to say. When you think about energy from the sun, that's the only thing that we need replenished on a regular basis, right? Every day the sun comes up, light shines down to the surface of the earth, warms us up, but unfortunately we can't trap and hold all that energy forever. It radiates back out into space, so we need the sun to come back up in order to re-warm us. Everything else, oxygen, right? All of our metals, iron, nitrogen, other gases like that, those are all closed systems. There's no spacecraft that's going to come from outer space and drop off extra oxygen for us when we run out. Like, you just have to recycle it or you're gonna run out. So when you understand a system as being open or closed, then again you can look at what's going on at the other individual parts of the system and study what's called the throughput. The throughput of the system is the energy and matter that flows into, through, and out of the system. And oftentimes this is governed by feedback loops. Positive and negative feedback, which I've got a couple different slides on for you here in a minute. But for now, I'll just tell you that positive feedback is kind of a self-perpetuating process. So whatever you make at the end is going to make more of itself over time. You could think of climate change as a positive feedback system. So as it gets warmer, it's going to continue to get warmer more and more and faster over time as we lose things like ice shelves and snow. Negative feedback is the exact opposite. Negative feedback is kind of suppressive change, where whatever you make at the end shuts itself down or stops itself by producing some sort of feedback that cuts things off. Okay, so once we look at positive and negative feedback, we also have to consider equilibrium, disturbance, resiliency, and a state shift. Equilibrium is the perfect balance between positive feedback and negative feedback, where a dynamic state of balance or homeostasis can be maintained over time. This system, or any system, should maintain a constant level of homeostasis at all times, right, in order to support life. Unfortunately, disturbances can disrupt that balance. A disturbance can be periodic. It could be something that's dramatic and sudden. It could be something that is slow and long term, but in the end, it's going to destabilize the equilibrium of the system. Bigger systems have more resiliency to these disturbances than smaller systems. So the size and complexity of the system often adds to the strength of the system, which is part of the reason why we haven't really seen much of an issue with climate change until now. As we've been dumping carbon dioxide into the atmosphere quite literally for generations, since it's going into the global atmosphere, it's going into a huge system, and due to its resiliency, it's been able to tolerate whatever we've thrown at it. It's getting to the point now where we're putting so much CO2 in so fast that the system can no longer absorb or deal with that, and we're starting to see more of a disturbance, leading to a state shift. So a state shift is a severe disturbance in which the system does not return to normal, but instead results in significant changes from its state variables. So just to kind of give you an idea of how we look at input, throughput, and output, let's take a look at this diagram. Okay, this diagram basically, or chart, lays out inputs as what is needed to start, throughput, the amount that can flow through the system, and output, what comes out. So if we go all the way back in these notes to that original picture of a waste to energy plant, I want you to think about what goes in, what's going through, and what's coming out, and see if you can fill in that table. Okay, what's your input, what's your throughput, and what's your output? If you need to pause the video for a second so that you can do that on your own, go right ahead, but I want you to try to fill that in before we just go forward and you get the answers for free. Okay, all right, so in terms of getting the answers, here's what I'm hoping you had. Okay, the input, again, still what is needed. Going back to that diagram, what do we need in order to make that waste energy plant go? We need water, we need waste, we need a turbine, heat exchanger, furnace, a boiler, storage area. The throughput, this is the amount that can flow through the system. We have a furnace that's burning waste at high temperatures, a boiler that's producing steam, a steam turbine that's rotating, scrubbers and filters that clean the waste gases to a point of 98% efficiency. And what comes out? Electricity, wastewater, some fly ash, some bottom ash, and some carbon dioxide. So how'd you do? Did you find all these parts? Okay, here's another example. Let's look at a fishbowl. Okay, so what's the input, what's the throughput, and what's the output? How is the system laid out in the fishbowl? Again, if you need to pause the video for a second so that you can lay out all those parts, go right ahead. If you're ready to move on, let's look at this. Okay, so in terms of this system, the sunlight produces or allows for photosynthesis. As the plants receive the light, they photosynthesize. That increases the plant's biomass, providing not only oxygen but food for the fish. The fish's biomass subsequently increases. That produces waste that feeds back to the plant, right, as the fish consume the plant. Okay, so as the plant biomass goes up, there is kind of a bad thing that could happen in this system, in that as the plant biomass goes up and it reaches the surface, the plant could actually block out its own sunlight, right? So these are all the parts of the system of the fishbowl. In any system, any system's basic characteristics we need to make sure that we understand all the working parts. The most important thing for us to deal with is the input, throughput, and the output. We also have some emergent properties for us to consider. Emergent properties are characteristics of a whole functioning system, that are quantitatively or qualitatively greater than the sum of the system's parts. All right, so that brings us to positive and negative feedback. So I've got a couple other pictures here just to kind of lay out what's going on in positive and negative feedback. I already defined them for you. But remember, positive and negative feedback are ways of nature dealing with disturbances and maybe maintaining homeostasis. In positive feedback, we're going to enhance or amplify change. Whatever your end product is going to create more of that end product. So I got a picture of this poor little polar bear sitting on some melting Arctic sea ice. The idea here is that sea ice has a high albedo effect. So as the sun shines against sea ice, the heat, the light energy is reflected back out into space, and subsequently the ice kind of acts as not only a reflector, but also as a cooling agent for our planet. Well, as temperatures go up and the sea ice melts, that reveals a dark ocean underneath. And as you know, now maybe you don't know, but if you know anything about albedo effect, the darker something is, well, the more heat it's going to absorb, right? Instead of reflecting stuff, it absorbs it. So the dark ocean actually absorbs more solar energy and becomes warmer. That leads to more ice melting, right? And with more ice melting, that means the temperatures go up and we get less ice. And it just keeps feeding and feeding and feeding into this cycle. Negative feedback is the exact opposite, right? It's a damper, a buffer to change. It holds the system in equilibrium and tries to keep them more stable. If you think about negative feedback, there's lots of examples that I could give you, but probably the best one, the one that I like focusing on more than anything, is your air conditioner. So when you set your thermostat on the wall at 70 degrees, if it gets too hot in your house, the air conditioner comes on, cools your house down, right? So turning on the air conditioning, producing cool air, right? Eventually that's going to bring your house temperature down and shut the thermostat off. So producing cold air doesn't lead to the production of more cold air. Producing cold air actually stops the production of cold air. That's negative feedback. And lots of other examples we could talk about in the book. Okay? Moving on from here, let's dive into some other terminology like time delay and synergy. Time delay is the time between the cause and its effect. Okay? So if I were to say, hey, smoking cigarettes gives you cancer, okay, there might be some validity to that scientific claim or just general statement. But aside from whether you agree or disagree with that statement, let's deal with the time delay piece here. If I were to smoke one cigarette today, am I going to have cancer tomorrow? The answer to that is no. There's a time delay. If I did in fact get cancer from smoking cigarettes, it could be a month, it could be several years before that cancer ever showed up. That's what a time delay is. Same idea can be applied to environmental science. So if I pump out a bunch of CO2 today, is the planet going to warm by like 5 degrees Celsius tomorrow? No. And that's part of the problem that we're facing when it comes to climate change and global warming. People put tons and tons of CO2 into the atmosphere every single day, and no one believes that climate change is happening because it's not 5 degrees warmer tomorrow. It might take a decade before we see that temperature change. And once we do see that temperature change, the problem is it's going to be too late for us to go backwards and fix it. Second thing is synergy. Synergy is a form of positive or negative interaction where two or more things basically create an impact. It could be a positive impact, it could be a negative impact. This slide is talking about the foul smell that ended up in LA as dead fish and hydrogen sulfide smells were blown by the wind into the city. But let me put it on terms of something maybe a little bit more real for you that everybody may or may not experience over the course of their lives. Let's say that I want to get in shape. Okay, so there's two big things that I could do to get in shape. I can eat right and I can exercise. Okay, so if I want to be in really good shape and I eat right, but I don't exercise, at the end of the day, I might get in shape, but it's going to take a lot longer if all I'm doing is eating right with no exercise. The opposite is also true. What if I just exercise, but then I still eat garbage every day? Am I going to get in shape? Probably not. What I need to do is I need to put 2 and 2 together. If I eat right and exercise, then the chances of me getting in good shape are exponentially better. Okay, so we've been through experimental design, we've been through models, system, positive, negative feedback. I'm going to give you a real-world example here that happened on the island known as Easter Island, once inhabited by the people group called the Rapa Nui. Now, realistically, I could just tell you to read this and answer the questions, but I kind of want to tell you this story. So let me take you through this story, okay? This is the story of Easter Island, and so if you look at this, Easter Island is right about here in the middle of the Pacific. There's Hawaii, and there's us, okay? So it's kind of, you know, out there in the middle of nowhere, so to speak. The island itself is probably most well known for these statues, right, that look like a giant bust, and maybe the Easter Bunny. Maybe that's what it's really well known for from the movie. I don't know. But more than that, there's a story about the people group, the Rapa Nui, that once inhabited this island. So let's learn about them. So our story begins in a place that's been called the most far-flung inhabited island in the world, Easter Island. 64 square mile speck, right, in the middle of the Pacific. Basically 2,300 miles from anywhere, right? Lo and behold, this island was remote but not deserted. From time to time, visitors dropped by, like the Dutch Admiral Roggeveen in 1722. He arrived on Easter Sunday, so guess what he named the island? Easter Island, okay? And he's the guy who left the first written account of the place and the people who lived there. So according to Roggeveen and other 18th century reports, some 3,000 islanders eked out a wretched existence by farming bananas, sugarcane, sweet potatoes from the poor rocky soil. The only fresh water came from like murky lakes inside volcanic craters. There was scarcely a tree on the island, and the people were small, lean, timid, and well, I guess basically miserable. Okay? Oddly enough, amidst the squalor, there were some surprises, like some 800 massive stone statues scattered all over the island, shoulder to shoulder, with their backs to the sea. So all kinds of questions were asked, like, how do we carve these things? How'd they quarry them? How'd they move them? How'd they erect them? Like, who did this? When the Europeans asked, where the statues had come from, the islanders basically gave this reply. They walked here. Failing to recognize sarcasm when they heard it, the Europeans embarked on a series of wild speculations that continued to present day. Spacemen set up the statues, like anti-gravity devices were used. Maybe this was a highly civilized lost continent that had sunken into the sea, leaving only Easter Island behind. Like, who knows? Since the islanders had either forgotten what happened or didn't feel like sharing, it was left to Western scientists and historians to kind of piece together, what took place. So basically what they figured out was around the year 400, Easter Island was colonized by Polynesians. Basically, various features of the islanders' skull, their blood types, their social system, language, and crops were all Polynesian. Pollen samples were taken from the lake beds that show the island was then thickly covered with vegetation, hacking out clearings from the jungle the Polynesians built, planted, and soon they enjoyed a typical Polynesian diet of yam, taro, breadfruit, banana, sugar, coconut, chicken, and Polynesian rat, which apparently is small but tasty. Their life was rich, their babies thrived, they populated the island with little effort, and in their copious spare time they carved some stone monuments, those heads. Okay? The statues were moved and set up with logs and rope. Recent experiments proved that when the statue was strapped upright onto logs, carved into sled runners, and raised onto a track of wooden rollers, a couple dozen people could, easily pull the thing. So they cut down a lot of trees, not just for rolling statues, but also for firewood and building material. And then by the year 1400, there was scarcely a tree left standing on Easter Island. Okay, what good are the trees, you might ask? Well, What happened on Easter Island when the trees got cut down? The roots died. The topsoil lost its anchor. 4 to 5 feet of earth eventually was washed away, and there was no quick way to replace it. Without the forest to absorb rain and replenish groundwater, the island's streams and springs dried up, the air became less humid, rainfall diminished, as fertile topsoil eroded, crop yields fell. There was no wood for houses, no fibers for fishing nets or sailcloth, no logs for canoes, and with no logs for canoes, no escape from the island. Rivalry for resources led to permanent warfare. Unfortunately, clan prestige was displayed by erecting statues. So the last trees were probably cut down in a frenzied effort, basically just to show off. Population peaked around 7,000 people in 1550 and collapsed so quickly that some 400 statues were left unfinished in the quarry. All the rival clans fought on. They pulled each other's statues down, and by 1860 every statue on the island had been knocked over. The point of the story is not that the people of Easter Island were somehow strange, silly, or different from anyone else. Quite the contrary. Like the rest of us, they were creatures of habit, and their way of life, farming, forestry, building, and display, was hard for them to change. Easter Island is a small island, and from its summit you could see the whole thing, so the person who cut down the last tree must have known there were no more trees. They still cut it down. So like the people of Easter Island, the people on the rest of the earth are rapidly changing our environment. Are we doomed to a population crash and a barren landscape, or can we sustain a green future for ourselves and the planet? I don't know. The question is yet to be answered. Alright, so that's the story of Easter Island. Now, here's what I want you to do. We'll skip over these. Just some pictures of how things went down on Easter Island. And I'm going to leave you with this slide. Okay? What are the strengths and limitations of models, you might ask? What happened to the people, the Rapa Nui on Easter Island? What's a system? What's a positive feedback, negative feedback, time delay, and synergy? Well, think about the story you just heard, and that's my question for you. Okay? You tell me, what are the strengths and limitations of a model? What happened on Easter Island? Where is the system in Easter Island? Where is the positive feedback, the negative feedback, time delay, and synergy? Alright, gang, that's your notes on Chapter 3. I'm Mr. Kennedy. You can always find these videos on my YouTube channel and handouts for these notes on our class webpage. I'll see you next time.